lesson is about complements and conditional probability, and also how we can use complements and redundancy to improve chances of something, actually. It's a relatively short lesson. So as we go through here, one of the key things that you'll want to look at is read carefully. I cannot stress that enough in statistics. At least one is a phrase, and at least one has exactly the same meaning as one or more. So if at least one means one or more, then the complement of that is none. The probability of at least one occurrence of a particular event would be equal to 1 minus the probability of no occurrences of that event. So when they say, what's the probability of getting at least one person who da-da-da-da-da? Well, the total probability is always summed to 1, so we can do 1 minus the probability nobody, da-da-da-da-da, whatever that is that we're dealing with. And we can use that complement to find things sometimes faster than we can deal with actually working this out. Square of Trade found that 6% of damaged iPads were damaged in bags or backpacks. If 20 damaged iPads are randomly selected, what's the probability of getting at least one that's damaged in a bag or a backpack? One damaged in the backpack is the event. So the complement of that would be none of them were damaged. Well, what is the chance that it's not damaged in that backpack then? 94% chance. Because if 6% of them are damaged, then 94% of them are not damaged in that way. And we've got 20 backpacks that we're dealing with. So what we can say is that 1 minus the probability that none of them were damaged in that bag or backpack. And I'm going to show you kind of 2 ways to calculate this out. I can do 1 minus, well, what is the probability it's not damaged? 94%. But I don't just need that to happen once. I need that to happen for every single one of those 20. So I'm going to raise that to the 20th. Now, just on a calculator, we'll just do that part first because I want to compare it to something else that you can see. So as I bring up a calculator then, we can do 0.94, that's the chance it's not damaged in this bag or backpack, and raise it to the 20th because I need that to happen for all 20 of them. And that's really using in the multiplication principle, and I get 0.290 in general. So that's going to be 1 minus 0.290. And then I can do my subtraction. 1 minus 0.290. And I get 0.71. How far should you take the decimal out? That just depends on what it says. Since that came out exactly, I'm going to say 0.771. Is this probability high enough so that we can be reasonably sure of getting at least one? Well, 71% chance. I mean, that's a pretty good chance, but are we going to feel sure? I'm going to go with no. It's not like it's in the 90-something percentile. If you're wanting to be more sure, what they need to do is get more backpacks, because as we test more backpacks and this value goes up, then since this is a decimal raised to that power, as that power gets higher, that result will go down, and 1 minus a smaller number will give me a bigger result. I'll bring up that calculator and just show that again, because what if they tested then 50 backpacks? That would essentially be 1 minus 0.94 raised to the 50th. And now they can be 95% sure that at least one of them, okay? 95% sure. So they just need to test more backpacks. Now, I said I was going to show you another way to do this, since there's only 2 outcomes. It either is damaged by that bag or backpack, or it is not. Only 2 outcomes can be considered binomial. And so I can go in here into this second of the vars, which let me make that a little bit bigger for you. The second function of vars is like the beginning of the word distribution. And I can go into second bars and scroll either up or down. It'll be quite a little ways to get to this binomial PDF with the P. See, there's one with a C. You'd want the one with the P. This will come up more in our next chapter. And I can say, okay, we're going to test 20 backpacks. The chances that this backpack was damaged in a bag or backpack is 6%. This 0 here would mean what are the chances, or what's the probability that 0 out of those 20? So none of them. That's going to let me calculate none of them. And when it pastes, it's going to look differently. It's going to take it to that home screen. It still has the numbers there. But notice that this result is exactly the same as that first result. So there are kind of two ways that you can do that. You can take the chances. Now notice the numbers were different because here we did what is the chance of it failing, and then none of them fail. Whereas up here we said what is the chance that it didn't happen, 0.94, and we said all 20 of them didn't happen that way. And so it's a very different way and approach, but you can get the same answer and then do 1 minus that. Anyway, we'll deal with the binomial more during our next chapter. A conditional probability is the probability that you find once you have some additional information that something else has already happened. And we have used this before, which meant the probability of B given A. That's normally how we read it. But that means that you're trying to find the probability of B happening after A has already happened. Now, there are a formulaic approach and an intuitive approach to making that happen. Because we had a formula in the past when we were looking at the probability of both A and B happening, you can see that right here where I've got my cursor going across. What we did to find the probability of A and B is take the probability of A times the probability of B given A had already happened. So it's like when we drew the card and didn't put it back. However, using some algebra, if you just take this equation here and you divide both sides of it by the probability of A, you actually can rearrange it to get how can I find the probability of B given that A has already happened. Now, you might use that formula because you might really need to, but you don't always need to. Sometimes you can use an intuitive approach. And so we're going to have a problem, and I'm going to kind of work it both ways so that you can see that, and we'll see that we get the same answer both ways. So if this is the question, one of 555 test subjects is randomly selected, find the probability that the subject had a positive test result given that the subject actually uses drugs. So this is our chart that tells us all the results, but this is the problem, and we're going to work it two ways. So first of all, by the formula. The formula down here in the lower left, the probability of B given A can be found by doing the probability of A and B over the probability of A. So now let's interpret that A and B based upon what's up here. When you look at the way this is given, this is the probability of B, and then the subject uses drugs is going to be the given, and so that's A. So that means to interpret the probability of A and B, we're looking at the probability the subject uses drugs and had a positive test result. So the subject uses drugs, that's on this row, positive test result, that's here, and that 45 is where this 45 came from. The probability that the subject uses drugs is our P of A, but the subject uses drugs is this entire row, and so that is where our 50 comes from, because the 45 plus the 5 is 50. And so that is this little section here. Now you can put those into your calculator. Just another tip about calculators is some of you may be getting used to this type of calculator. We can use alpha y equals, and you can use it more than once to enter complex fractions. So here then I can put my 45 over 555. I know that's too small for you to see right now. And then I can go back to the denominator and do that same thing again. Alpha y equals, enter, and it's going to let me, again, put another fraction in there. So I can go 50 over 555. And some of you might think, well, why would we do that? We know the 555s are going to cancel. But you know, that just kind of depends on how comfortable you are with fractions. Okay, so that's 9/10. 9/10 as a decimal is certainly going to be 0.9. You could also simply put parentheses around each fraction and then use division. But anytime, then this used to be the only choice we had for doing this on calculators. They didn't have fraction keys or that option where we could make it type like it. Anytime you type a fraction and you're using that division key, just put parentheses around that fraction by itself. Okay, so we get the same result either way. And that's what this is. Now, does it need to have the extra zeros? Not necessarily. It depends very much on your instructions. Read carefully. Another approach, an intuitive approach, would be just to consider the fact that it's given that the subject uses drugs. If the subject uses drugs, why are we looking at the rest of the chart? Only look at this row of the chart. And again, that's where the 50 comes from. So that added up to 50. But then out of that row, only looking at that row, we're looking for the positive test result, and that refers to this 45. And then so you can simply say 45 out of 50, and when you divide that out, that's 0.9. So it seems to me that that's definitely the easier approach to take. Occasionally you might find a problem where you don't have enough information to do it this way, and you have to use the formula. But if you have all the information and you just focus on what's already given and just quit looking at anything else, the moment this says it's given the subject uses drugs, that's the only row we want to look at. This one has absolutely nothing to do with our information then. And you can do some of your work a little bit faster that way. You have to pay close attention to which one is given. The one that is second is the one that is given, and it makes a difference. The probability of B given A is not expected to be the same as the probability of A given B. I mean, there's a fluke where it could be the same, but you should not count on that, and that sort of confusion is called confusion of the inverse. If you look right down here, the probability of dark given it's midnight and the probability of midnight given that it's dark, well, that would mean if it is midnight, you've already been given that it's midnight. If it is midnight, you know the sun's not out, there's a really good chance it's dark, okay? I mean, you could count on a moon perhaps, but we would still call it dark outside, even if there's a full moon. So when it is midnight, we expect it to be dark. On the flip side of that, just because it's dark doesn't mean it's midnight. Okay, it is dark for several hours at night, and it's only midnight for this minute. So the chances that it's midnight just because it's dark is very low, while the chances that it's dark when it's midnight is very high. So you've got to be very careful which one is given and focus on that. Related to the way we do the work, but still a different topic, is redundancy. Redundancy increases liability, and that means it essentially means if you have a backup plan, it's more likely to be successful. So we have these two quick little examples here. When a twin-engine plane has an engine fail, it can still fly. When a person loses an eye in an accident, I hope that would be a tragedy, but he or she can still see because we've got two eyes. Whenever we can duplicate something, then the chances of full failure go down. One example where we see that this would be really important is in the case of hospital generators. Hospitals have backup generators so that if the power goes out, they can still function. So assume that an emergency backup generator fails 22% of the time when they're needed, and a hospital has 2 backup generators. Find the probability that both generators fail during the outage. Well, again, I'm going to do this like we did earlier. The probability that one of them fails was 22%. But since I have 2 of them, I'm going to do 0.22 times itself, which is just squared. It's a little bit less writing to just use that power. And then let me pull up my calculator. And we get 0.0484. 0.0484. Now again, I might want to round that to something else based on instructions as you're doing your online work. But what we're looking at then is this is a little bit less than 5%. What's the probability both of them will fail? A little less than 5%. Find the probability that at least one of them works. Okay, here's another thing to just notice. This question was about, oh, I hate it when I scribble and I mean to highlight. This question was about fail, and this question is about works. So we're doing kind of the opposite, right? If you think about it like that, the probability at least one of the generator works is exactly the complement to both of them failing. If they don't both fail, then at least one works. So that means I can do 1 minus the probability that they both failed. Because, again, this one and this one both fail versus at least one works. Those are complements. So 1 minus 0.0484. Here I can just hit 1 minus my answer is 0.9516. Oh, excuse me, wrong line. Now this one, is the hospital in a good situation with the generators? Well, that's a little bit interpretive, but personally, I am not quite satisfied with 95%. I want them to get it closer to 100%. I want to know that the hospital is going to be able to make it. So I'm going to say, no, they need another backup generator. I'm just going to say right now they need more. And then let's figure out how many more they need for us to be comfortable, okay? Again, I got this 0.0484 by doing the possibility of failure squared. So 1 minus 0.22 squared. You can see what that was. So that gave me 95%. What if I have 3 backup generators? Then essentially then I could put a third. What is the complement of all 3 of them failing? That would mean at least one worked. Well, that brings it up to about almost 99%. 1 minus 0.22 raised to the 4th. Okay, now that is really close. We're not going to get to 100% because there's always a chance they could go both down. They need to get at least 1 more generator, preferably 2. So they need, I'm going to go back here and say 1 to 2 more, because 1 more would bring them up to rounding to 99%, but 2 more brings them rounding to 100%, even though it's not exactly 100%. So anytime you have more backup options, your chance of success is better, and that's what we're dealing with on redundancy. So that finishes up this lesson. Please get in touch with me if you've got any questions.